Hi guys, so as we enter our final week of studying systems of equations, we're going to dig into systems of inequalities. Now, systems of inequalities are a really different beast from systems of equations. There are some things in common, but you'll notice that we solve them completely differently. There aren't very many good algebraic ways of solving systems of inequalities. There's graphing, and there's verifying your graph by guessing and checking. So we model those solutions really differently. We teach systems of inequalities because they are actually very real world. You run into situations that can be modeled in systems of inequalities often. And they're used really often in computer programming, which is where we'll do a project with this toward the end of the week. So I want to start off by reviewing what we already know about inequalities and how to solve them and graph them. So for example, you know about inequalities that have one variable. This is an example here where a fictional school club is buying shirts for a performance, and the shirt company charges an upfront fee of $35 for the design, and then it's $15 a shirt. The club has a budget of $350. So the implied question is, of course, how many shirts can they afford to buy? Now, a budget means you can spend your whole budget. You can spend the 350, but you can also spend less. You just can't spend more than your budget. So the whole situation is an inequality that can be modeled in this way. If you do 15 times the number of shirts plus the $35 upfront fee, that amount has to be less than or equal to 350. You can spend less than your budget. You can spend up to your budget. You just can't spend more. So to answer the question of how many shirts we can buy, we can solve this just like we'd solve a linear equation, and then we graph it as a whole set of solutions. So to solve it like a linear equation, first we'd subtract 35 from both sides. So that's 15x is less than or equal to. And actually less than or equal to you can do in a Google Doc by doing insert special characters. And then if you type the word less, you get this little guy right there. Okay, less than or equal to 315. And then if you divide both sides by 15, you get 21. So x is less than or equal to 21. So that's how many shirts you can afford to buy. Now, when you plot a inequality on a graph, remember there's an open circle if that value is not allowed, and there's a closed circle if that value is allowed. So for a less than or equal to situation, you would use a closed circle. So I'll put one of those on 21. And then since it can be less than or equal to that, you draw a shade in this part of the graph going from 21 on down. And let me just make that closed circle a little more distinct there. So a closed circle on 21 because that value is legal, and then an arrow pointing that way. One special note when you're using negative numbers in inequalities, let's say we have an inequality like this, negative 5x is less than 30. To solve this inequality, we could solve it just like a linear equation, and so to do so, we'd divide both sides by negative 5. So then we'd say x less than negative 6. However, if you actually test values less than negative 6, you'll find out they don't work. So example, try x is negative 7. Negative 5 times negative 7 is 35, and 35 is not less than 30. So this solution to the inequality doesn't work. It turns out whenever you multiply or divide by a negative number to solve an inequality, you need to reverse the direction of the sign. So x is not less than negative 6, x has to be greater than negative 6. Try it by testing any value greater than negative 6. Try negative 5. Negative 5 times negative 5 is positive 25, and positive 25 is less than 30. So you have to switch the direction of the inequality sign every time you multiply or divide by a negative number. To plot this one, we would need to put an open circle on negative 6 because it's not legal for x to be exactly negative 6. If x were exactly negative 6, this inequality would be equal to 30, not less than 30. So we put an open circle on negative 6, like so. And then I'll make my line a little thicker. Nope, looks like I'm changing the color. There we go. And then it can be anything greater than that. So we put an open circle on negative 6 and then draw a solid arrow going in that direction. Let me make my circle a little thicker. So that's what that plot would look like. Open circle if it's greater than or less than, closed circle if it's greater than or equal to or less than or equal to, and then you draw a shaded arrow in the direction of the solution set. So hopefully that brings back some memories for you. And I want to move on to the next topic, which is that you can solve linear inequalities in two variables, and you can graph them. It's a similar technique to what you do when you just have one variable. So here's a system of not a system, it's just an inequality that has two variables. In this situation, so there's a homeowner that wants to install grass sod and flower beds, and I'm going to grab my pen so I can draw. I'm going to pick a color. Sorry, give me a moment. So in this situation, she can install a certain number of square feet of sod and a certain number of square feet of flowers. Her total budget is $3,000. So again, she can spend $3,000, but then she can also spend less than $3,000, and that's still valid. Since sod costs $2 per square foot and flower beds cost $12 per square foot, and I can see here sod is on the x-axis and flower beds are on the y-axis. So we're going to use x to represent the square feet of sod and y to represent the square feet of flower beds. Our equation would look like this. We would write 12y plus 2x equals, or not equals, has to be less than or equal to 3,000. Okay. So if that's true, I'll show you a technique for how we can make a plot of this solution set using a two-axis grid. So first thing you do is you're going to graph the line as if it was just a line. Since this is written in standard form, you can graph it using the x and y intercepts. And the way you do that is you plug in 0 for each variable and you figure out the coordinates for the other graph, or the other axis. So for example, let's plug in 0 for y. If y is 0, then we'd figure out how much it would cost to cover our whole lawn with sod. 3,000 divided by 2 is 1,500. So the point 1,500, comma 0 is on the graph. Next, we plug in 0 for x. If x is 0, then 12 times y is 3,000, and y would be 250. So the point 0, comma 250 is also on the graph. You see how in standard form it's really easy to just find the x and y intercepts, just plug in 0 for one of the variables and solve for the other. So I'll put those 2 points on the graph. Here's 1,500, 0 right there, and there's 0, 250 right there, and we'd connect them with a line. So I'm going to grab a line tool and do that. Now, when you're solving a system, or when you're drawing an inequality in two variables, I keep saying system, this is not a system. The rule of thumb is if there's a less than or equal to or a greater than or equal to, you draw a solid line because values on the line are fine. You can have any value on that line. But if you have a less than or a greater than, you can't actually have values right on the line. You can have any values on one side of the line. So in that case, you draw the line dotted instead of solid. So to finish graphing this, we also have to note that any value on the line is okay, but we can also have values that aren't on the line but are on one side of it. So pick a value that's on one side of the line or the other. Like let's say 200, comma 100, and I'll just put a dot right there to take a note of it. Let me grab a freehand. Okay. So at 200, comma 100, that's 200 square feet of sod, 100 square feet of flower beds. So 12 times 100 is 1,200, and 2 times 200 is 400. 400 plus 1,200 is 1,600. That is less than or equal to 3,000. So this point is in the solution set. You could also do like 650. So if 50 is y, 12 times 50 is 600. And then 600 times 2 is 1,200. 1,200 plus 600 is 1,800. This point is also a valid point. You can see how anything like kind of below the line is a valid solution. So you can shade in everything below this line. You can get any number of sod and flower bed combinations that are on the line, or you can get any number of sod and flower bed combinations that are in this shaded region, and that's a valid solution to this inequality. That's the solution set for the inequality, and this is how you graph it. So again, greater than or less than would be a dotted line. Greater than or equal to, less than or equal to, solid line. And then you shade in the region of the graph that makes the inequality true. Okay? So I think that there is, let me erase my drawings here. All right. There are a few examples down here, so we'll just like do a couple of these real quick, and then I'll point you to the Khan Academy questions. So for example, y is greater than x. So we're going to graph the line y equals x, and since this is a greater than, the line is going to be dotted. Y is not actually allowed to be equal to x. Y has to be greater than x. So let's make a dotted line at y is equal to x. That's the set of points where the y is equal to the x. So like 1, 1, 2, 2, -1, -1, and so on down. There's the line. Now we have to shade in the region where y is greater than the x. So for example here, y is 1 and x is 0. Is 1 greater than 0? Yes, it is. That's true. So therefore, the area that this point is in is the area that's shaded. So you can shade in this region, and that's the solution set for y is greater than x. Dotted line, and you shade in everything like above the line. This one would be basically the same, except the line would be solid, because y can be equal to x, or y can be greater than x. Okay, let's take a look at one example down here. Let's say in this example, y must be less than 10x minus 200. So this is a line written in slope-intercept form. Our graph isn't scaled, so I just get to pretend what the scale is, and I'll imagine my scale is in 50s. So 50, 100, -150, -200. Here's the y-intercept. And since the slope is 10, that means we go up 10 every time we go over 1, or we can go like up 4 and over 2.5, or up 200 and over 20. So, you know, we'll cross the x-axis somewhere here, and then we'll end up somewhere up here. Now this is going to be a dotted line, so I'll just make a line of dots going down here. So again, y-intercept of -200, slope of 10, okay? And then I need to shade in the region where y is less than 10x minus 200. So pick a point on the graph. Let's say we do 0 on the x, positive 50 on the y. So we'd plug those numbers in. 50 less than 10 times 0, which is 0, minus 200. And we ask ourselves, is that true? That's not true. 50 is not less than -200, so this point on this side of the line is not in the solution set. But maybe let's try 100 on the x, 0 on the y. So 0 less than 10 times 100 is 1,000, and 1,000 minus 200 would be 800. That is true, so this point is in the region that you would shade in. So you'd shade in this part, this side of the line, that half of the graph. And that's the graph of that inequality. Y is less than 10x minus 200. For your practice problems for this problem set, you will do some Khan Academy exercises. The first set is just graphing inequalities on a number line, one variable. Remember, open circle if it's greater than or less than, closed circle if it's greater than or equal to or less than or equal to, and then shade in the part of the line that represents the solution set. And then you'll do one problem set on graphing two variable inequalities using the dotted line or the dashed line and shading in the half of the graph that represents the solution set. Okay, and then in the next lesson, we'll start to talk about systems of inequalities and how we solve those. Thank you. Have a great day.